This is episode 694 of the People Behind the Science podcast. I'm your host, Dr. Marie McNeely, and today we are excited to rebroadcast our interview with Dr. Dan Goldman, originally published on June 22nd of 2015. Listeners, Dan conducts research on how animals like lizards, crabs, and insects move in complex natural environments, such as sand, leaves, and grass. His work focuses on the interactions between the musculoskeletal systems of organisms, their nervous systems, and the materials with complex properties. And the discoveries he makes are helping to develop robots that are better able to move in these complex natural environments. In our interview, Dan shares wonderful stories from his life and research. So I hope you enjoy this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. I am excited to be here today with Dr. Dan Goldman. So, Dan, welcome to our show today. How are you?
I'm good. Thank you for having me.
Wonderful. Well, thank you for joining us. And I'm excited to introduce you to our listeners. So listeners, just a little bit about Dan. He is an associate professor of physics at the Georgia Institute of Technology. He received his PhD in physics from the University of Texas, Austin, and then went on to conduct postdoctoral research at the University of California, Berkeley. Now, Dan is an esteemed scientist here. He has received many awards and honors during his career, including being named a Georgia Power Professor of Excellence and receipt of the Presidential Early Career Award for Scientists and Engineers. He's also received a DARPA Young Faculty Award, an NSF CAREER Award, and the Georgia Tech Fund for Innovation in Research and Education Award. Dan's work has been featured by the New York Times, NPR, BBC, Discovery Channel, National Geographic, and many other media sources. And Dan is here with us today to share his journey through life in science. So Dan, we are looking forward to getting to know you, both as a scientist, but also as a person. So can you start by taking us to your non-scientific side and tell us what you like to do when you're not doing science?
Thank you again for having me on your program. These days when I'm not doing science, I am attending to my 22-and-a-half-month-old daughter, who takes up all available time and resources when I'm not doing daily scientific research, writing, teaching, etc., etc.
Wonderful. So what's the favorite activity right now of your daughter?
Let's see. So what do we do these days? Well, we play guitar. I've played guitar not well, but have played most of my teenage and adult life. And my daughter likes to also play her little tiny Minnie Mouse guitar along with me.
Awesome.
So we sing songs like The Wheels on the Bus Go Round and Round. We sing that over and over and over while I play, and she plays as well and sings.
Well, father-daughter duets just sound awesome. A great way to spend your afternoon.
Yes, until she gets bored.
Right. Which there's perhaps a short window in there. Well, Dan, wonderful to get a glimpse of your life outside of the lab. And next we are going to turn to your scientific side. So can you tell us a little bit about how you describe what you do to someone who might not be familiar with science?
My research program here at Georgia Tech in the School of Physics is one which is really driven by problems in organismal biology for the most part. And what I mean by that is we're interested in studying how animals that are of the size of lizards and snakes and crabs, move around in complex natural environments. It is kind of biophysics done at the organism scale, roughly speaking.
Well, very cool. And I'm excited to dive into your research a little bit more. And I think this is a unique area that I haven't met many people that are really studying this interface between organisms and their surfaces. So very cool. Now, let's take a pit stop here, though, and talk about motivation. I think scientists keep so busy with the work that they do and the life they're trying to balance outside of it that sometimes you need a little pick-me-up, a little piece of motivation. So can you share with us your favorite motivational or inspirational quote, Dan?
That's a good question. So what's interesting I've been writing a review article recently on what I'm calling robophysics, which is the other side of the research that we're doing these days, which is actually making robot models of the organisms we study and using those to answer questions about basic biology of movement. And so we just wrote a review article. And in that review article, I put a couple of quotes which are likely relevant to not only my research now, but have sustained me through the years. And they come from a mentor of mine, and I was an undergraduate at MIT, a guy named John King, who was a physics professor who had been at MIT for 50-some years, maybe less when I was there. Mm-hmm. Sadly, he passed away just last summer, but he had some very nice quotes, and one of them was to always make mistakes quickly. And I think that that's something I've tried to instill in my students, that often when we're doing experimental research, what we think is going to work typically does not work. And so to get something to work, then it's important to figure out why it's not working as quickly as you can and then move forward. And that's sort of been an inspirational quote. His other quote, which he put into a nice review article on his education efforts, was that there's no substitute for hands-on fooling with the real stuff, something like that.
Yeah.
That hands-on research is an important component of scientific research. And that's another quote that inspires me, I guess more in the research sense.
Well, fantastic motivational or inspirational quotes there from your mentor, John King. I love this idea of making mistakes quickly. I think you make so many mistakes in science. It's just part of the process, but not dwelling on them and quickly moving on to the next thing to fix it, I think is a really important point. And I love this idea of hands-on science. And I think that's so important at all stages of your career, not only when you're first getting excited about science, being able to get in the lab, but also really maintaining your passion for it as you advance in your career and kind of feel like you're getting out of the lab more and more. Well, wonderful motivational quotes. And we mentioned one of your mentors here, John King at MIT. Are there other people who really stand out in your mind as people who've motivated or inspired you along your journey?
I've been very lucky. And I think that in terms of my scientific career has really enabled me to succeed in whatever level of success I've had, in large part due to, I think, either listening to or maybe just not ignoring or over time absorbing the lessons of my not only undergraduate mentor, Professor King, but my PhD advisor, Professor Harry Sweeney, as well as my postdoc mentor not so long ago, 10 years ago when I left my postdoc roughly, Bob Full. But each of those scientists really helped instill certain bits of scientific philosophy and ethic, and it helped form my research program. And so I owe a lot to these folks.
Wonderful. Well, I love hearing about mentors and people who've inspired scientists along their journey. I think this is one of the fun aspects of the career as well, is that now you get to play this role for your students. So can you tell us a little bit about how this mentorship factors into your current day-to-day career?
Well, I can say that I learned, obviously, not only how to do science from my mentors. Like I said, I got lucky that they were such caring mentors. I think that they also had my future career in mind, which I think is an important thing and a lesson I try to think about daily as I interact with my students and postdocs. I can tell you a funny anecdote, actually, that goes back to when I was in high school, and it has to do with mentors.
Sure.
When I was in high school, I worked in a biology lab for a summer. I grew up in Richmond, Virginia, Commonwealth University. And the guy I worked with, a guy named Mike Holmes, had, I think it was him, invited a very famous biologist named Max Perutz, who was, I guess, the first person to figure out the X-ray crystallographic structure of hemoglobin.
Oh, wow.
If I'm not mistaken. Anyway, he gave a colloquium at VCU, and they invited me to come and listen. And, of course, they didn't know what's going on, but
right.
It seemed cool. And then there was a little reception afterwards. They were invited me to go to the reception. And Perutz must have been in his 80s. He seemed ancient to me at the time. And they introduced me at the colloquium at the little reception. Said, well, this boy is going to MIT in the fall. Do you have any advice for him? Mm-hmm. Everybody kind of leaned in and listened in a very kind of low voice, low tone. I sort of felt like I was talking to Yoda. He said, find a good mentor. And That was it. That was the advice.
Wow.
I had no idea what he meant. Nobel Prize winning guy. Who knows?
Right.
And that just seemed like non-advice to some extent. And only now, as I move down the road here in time, have I understood what that really is about. And there couldn't be better advice.
Well, it sounds like you took his advice to heart, perhaps inadvertently then in that case.
Yes.
Well, let's rewind a little bit. So you mentioned this experience in high school that you were working in a laboratory over one summer. Can you rewind back a little bit further and tell us what got you interested in science to begin with? What is one of these early memories of you first having that spark lit?
It turns out that what I'm doing now in my career is in some sense a kind of formalized and sophisticated version of what I've been doing since I was 10 years old, I guess. When I was a kid of that age, I really was into lizards and snakes. I wanted to be a herpetologist. I'm reminded of this by friends. I wrote it in my middle school yearbook, Dan Goldman, herpetologist.
Wow.
That's not something to say wow at. So I, for some reason, had this obsession with cold-blooded animals. I went to pet stores and I hung out there and I had lizards and I kept them in nice terraria and et cetera, and studied everything about them and wrote letters to textbook authors and even got some responses about what their favorite lizard was, this kind of stuff. But somewhere along the line, I decided, and I think it was a friend's dad showed us something about relativity, a little simple calculation when we were early high school. I said, boy, physics seems like it's cool and you don't have to memorize as much as you do in biology, and there's some sort of beauty. I didn't know what I was saying probably, but some sense of universal truth and beauty associated with it. And it seemed like a good thing to do. And plus it had math in it, and I kind of liked math at the time. And so I ended up over my high school years being interested in science and math. But when I went to MIT, I said, well, I want to be a physics major. And I wanted to be a kind of theoretical physics major. MIT had different tracks. You could take the theory version of intro physics, the regular version of intro physics. Then there was a new version of intro physics that had come online for experiments. And that's where I met Professor King, who was trying this new innovative curriculum, basically hands-on intro physics, where each student got a kit of parts. And in our dorm rooms each week, you kind of did a hands-on experiment. I remember one in particular, you made a Hertz spark gap oscillator and detected the radiation with your radio. Anyway, I entered that class because I happened to run into him at a class demo fair and saw that they were measuring gravitational acceleration by dropping a metal ball, and opening and breaking a circuit and then measuring the time, circuit charge. And I just thought that was the coolest stuff.
You were hooked. Yeah.
And so that's where I decided to do experiments and worked in his lab for 3 years. And I didn't do anything of consequence scientifically, but I sure learned a lot. And he put up with me for 3 years, learning to make less of a mess year after year. So that was just a lot of fun. And that was kind of the origin. And then when I was going to graduate school, I was not very inspired by anything. I sort of burnt out, but had read James Blake's book on chaos and said, oh, that seems like cool stuff. So I applied to go to the University of Texas at Austin, where Harry Swinney, who was mentioned in the book as an experimentalist studying chaos and fluids, was. And I got in and went there. And after some hiccups in graduate school, which I'd be happy to go into because I think it's instructive for any students who may be out there listening.
Sure.
I ended up in his lab doing what's called nonlinear dynamics, which is kind of a broad catch-all for systems which have interesting dynamics. Could be fluid systems, could be atomic systems. I happened to study granular materials. But as I was coming to the end of my PhD and deciding whether I wanted to go to a postdoc or to go to industry or just go and be a musician, who knows, I said, well, a lot of my colleagues are going into biophysics, but the kind of biophysics they're doing, which is at that time a lot of molecular and cellular biophysics, doesn't really appeal to me so much. I wonder if there's any opportunities in the kind of biophysics or biology that I liked as a kid. And it turns out that there was a group of dynamical systems types who were starting to interact with a biologist named Bob Full, working to kind of understand locomotion, movement of animals through dynamical systems theory and experiments. And I said, boy, this sounds right up my alley. And I visited, and the lab looked roughly similar to what I had experienced as a graduate student with hands-on tabletop-sized experiments. And so I went out there for 4 years and learned some biomechanics and biology. Then while I was there, my mentor Bob Full helped me realize that there was this beautiful intersection of the world of biomechanics and neuromechanics is what we're calling it now, and these kind of complex materials. And nobody knew much about either the biology of what was going on in animals that live in deserts or the physics of the kind of interactions that are important to move in deserts. And that was kind of the origin of my faculty job.
Wonderful to hear a little bit about your story. And I'm going to make you rewind and revisit these hiccups in graduate school. We always like to talk about challenges, the struggles scientists face. So tell us a little bit about these.
Since I'm feeling overly honest today, you have a soothing voice, which makes me want to tell you things. That's why I think you're so good at this. I guess as a high school kid, I had advanced math classes and I was very focused. I went to MIT and I got there and I did well in the first year or so. And then I started to get a little bit burnt out, I guess. I didn't know that's what was happening, but I just didn't have the same drive and push to do classwork. And it just wasn't so exciting to me. But the laboratory work was exciting. And I met Professor King's son, who also, his name was Ben, who also played a very important role in my development, although he would not know that. And he was a master mechanic and really showed me all sorts of interesting things about building and designing physical systems. And I said, oh, that seems like something that would be more fun than just taking classes. But I decided to go to graduate school anyway. Mm-hmm. And Professor Sweeney, who was very famous, still is, accepted me into his lab, which was a big honor. And I was there for a couple of weeks taking classes as a first-year graduate student at Texas and not particularly inspired and not doing particularly well. And then I realized that I didn't really even want to be there anymore. So I marched into Sweeney's office one day and said, I'm quitting.
Oh, wow.
I just left and I dropped out of graduate school. He still tells this story, so I figure it's okay to tell. Dropped out of graduate school and went and did various odd jobs for a year, fixing pressure washers and working on a printing press and this sort of stuff. And then realized that there were a lot easier ways to make a living than doing manual labor. And it looked very strange for a kid from MIT to be doing this anyway. So I said, well, let me see if I can get back to graduate school. They let me back into graduate school. And then I marched into Sweeney's office again and said, I would like my position back, please. And he said, nope.
Really?
Yeah.
So what did you do?
Well, so then I don't know what I did, but I went back and did my classwork for a semester and didn't do well in a particular class. I think it might have been Stat Mech. And went back to his office, like at the end of that semester, and said, I want to work in your lab. And he said, how'd you do in your classes? And I said, I got it. He said, oh, nope, no chance. So I then did well in my next semester and then went again to him and said, I really want to work in your lab. And in fact, it's very interesting. I was working in the lab of another professor, John Marker, condensed matter. And I was enjoying what I was doing. But I went to him and he told me something which also still resonates to this day. I said, I really would like to try to work at Sweeney's lab and do nonodynamics. And so I've enjoyed having you here, but science is a passion. If you're not passionate about doing what you're doing, then there's no reason to stick around in a particular area. So he gave me his blessing. So I asked Sweeney again, and he said no. And then in despair over a spring break, I decided I would cook up a little experiment in my apartment, and I created a little granular material shaker, which I could shake particles of different size, kind of it would fit in your hand, and brought it into him. And he and another guy who's now a colleague of mine, a guy named Paul Lumenauer, who was a graduate student, looked at it, and Paul put in a good word for me. And so he said, well, we'll give you a try for the summer. And so then I managed to do well enough to stick around for the next 6-7 years in his lab and get my PhD. But it was touch and go. So I thank him. I had to ask 3 times, but he eventually let me back in.
Well, I think that persistence is very impressive. I think a lot of people, once you hear no the first time, you sort of give up. But I love that you kept asking, you kept going back and saying, no, this is really what I want to do. You didn't settle and join another lab, which is doing great science, but not something you're excited about. So what really kept you going and kept you going back to continue trying to get back in that lab?
I have no idea. I think that in the end of the day, and I tell my students this, doing science obviously has to be a passion. I say obviously because we know it, but students don't know that typically. And I have discussions with students who say, well, I could go off to industry and I could make this money and I could do. And in fact, it's interesting. When I was finishing my undergraduate degree, I was interacting a lot with a bunch of Russian PhD students who had come over. This was in the early 90s. And so this was the time when a lot of brilliant students could get out of Russia. And they came to MIT and doing their PhDs. And now most of them at this day are on Wall Street, doing financial things, making lots of money. And that's fine for them. They're happy making money. And they asked me why I stuck around physics. And again, the only thing I can answer is it's a passion, and it's something that was sort of deep in me. And why I wanted to do non-dynamics, there was something, or work with Swinney's group, there was something in that group and the style of science which sort of called to me. And I don't know what that is, but maybe it was related to the things I used to read about fractals when I was in high school and middle school and write little computer programs. Maybe, I don't know, but it clearly was sort of in my gut, and that is the best I can say.
Well, something ingrained in there. I like it. And I think that's really the first step of getting through this challenge of figuring out what you want to do, is figuring out what you're passionate about. And it sounds like you had a really good sense of that pretty early on. And then it's just sort of deciding to commit to it that I think is the other half of the challenge there.
Yes, that's right. And realizing that it's going to take hard work no matter what you do. Persistence and hard work and sweat and suffering are critical aspects to all of this. But without the passion and the joy,
it's a long road. Yeah.
It's a road that may end. There's other things to do. There's things you can do which will make more money and have more free time, et cetera, et cetera. These are tropes which everybody knows. It may even be true, but in the end of the day, I feel lucky that I have, in my opinion, the best job in the world and wouldn't trade it for anything.
Well, I'm so happy to hear you say that. And I want to hear now more about this current position and what you're working on. So can you tell us in a little bit more detail about one of these projects you're so excited about?
So like I said, broadly, my group is interested in understanding these days movement. And movement to physicists often seems like, well, you study intro physics and it's either that there's no forces, so things just move forever, or like in a rocket ship, spew out some material and the reaction forces push you the other direction. And there's another class of movement, which is what some people call self-propulsion, which basically means you have to deform your body in the appropriate way. Beat your wing if you're a bird, or even a fish to some extent. Wiggle your body if you're a snake. Cyclically move your legs if you're human, which requires effective interaction with the environment to generate forces which can propel you. And these questions are not at all trivial. They're not like rolling a ball from A to B. And so this sort of intellectually fascinates me from the kind of point of view of you can generate locomotion, like I said, with a very simple system. I just give a block a push across the table, but that's sort of cheating. If I want the block to move itself, I have to figure out how it's going to actuate. Its internal degrees of freedom of actuation and sensing are necessary for that. I have to decide how I'm going to push on the environment so that it pushes back on me in the appropriate way. And the amusing thing is this immediately runs into questions. Even in the 21st century, we have no clue how to answer. For example, if I am a little lizard running on sand out in the Mojave Desert, one that we study, observing that little lizard and want to tell you the kind of forces that are generated when its large feet hit the sand, I can't do that yet in the same way I could do with fluid. And so the animal moves, but we don't know how. So this is sort of an interesting question, not only from the kind of questions of the dynamical system, which is the organism, how do all the complex components integrate to affect what looks like sort of seemingly trivial, just rapid movement, and how do those internal bits interact and generate propulsive forces with the environment to move it. So these are really interesting questions to me.
Absolutely fascinating. Now, I study locomotion, but more at the human level and ignoring completely the environment, just sort of the neural control. So tell me a little bit more about how you select the environments and the organisms you're going to study. I think there are so many different options out there. How do you choose?
That's a very interesting question. And as you know, and scientists who are listening know, but maybe the students who are just starting don't. Often the hard part in science is figuring out what the interesting question is. And once you've even started something, what's the interesting part of what you're doing? And that's a matter of taste. Some people have exquisite taste. I've happened to work with mentors who have, and I hope to one day have that kind of taste.
Right.
And it really is then deciding what's the interesting nugget that you can pull out. When I got into this, I said, well, here's animals, here's sand. It seems like there ought to be interesting questions. Mm-hmm. And only after 8 years of working on these problems have we realized, in fact, that not only are there tremendous diversity of organisms out there that utilize the physics of dry sand, we'll just stick with dry sand for now, to go about their daily business by burrowing in the sand, by generating fluid-like states to run rapidly across it. But the questions that we can address turn out to be, at first blush, very complicated and seemingly intractable. But after 8 years of work, we've realized that the kind of systems we've been studying have nice properties that make them amenable to detailed study in the way that I like to study, which is do laboratory experiments, create models, and go back and forth between the models and the experiments, making predictions and testing predictions. And one can do that kind of in-house in these granular locomotion systems, which was a big surprise to me because when I started, I just thought, well, a lizard swimming in sand, which is what we spend a lot of time studying, is just sort of a weirdo system. It's cool. Mm-hmm. No one's ever seen now these little lizards, which are ubiquitous in dry deserts, swim around in sand. But okay, once you get beyond the fact that nobody's ever seen it, who cares? Well, it turns out that the who cares is that we can actually, and you might be interested in this, really get at fundamental neuromechanical questions of movement by studying these little animals in these environments. It just turns out that the animals have certain simplifying properties. Environments have certain simplifying properties. When you put them together, you can do detailed back and forth experiment theory in a way that is harder, I think, in other organismal locomotion systems, actually.
Well, very, very interesting. And I want to back up to a point where you mentioned previously you had done some work in what we call robophysics, which I think could be the title of a movie. It's so awesome.
Well, it's the title of a review article, which I just submitted to Reports on Progress of Physics. So we'll see if it flies.
Awesome. So tell us a little bit about the robotic side of what you do.
Yeah, so after that kind of long-winded discussion of the animals, the nice bit about this area of science that we're in, a number of us are in, very few physicists at this point, but a number of biologists and engineers, and this will lead into kind of one of the projects I'm most excited about right now, is that often, like I say, we don't have the equations of motion which govern how a foot or limb or body part interacts with the sand or the material. So there's another way to model organisms, and that's to create robot models of them, which have the benefit of one being in the real world is also a drawback because it's harder to vary parameters in the real world than in silico. But the beautiful bit is that they get to interact with real materials. So even though we don't have the physics equations, we can simulate the motion in the real world. It's kind of a physical simulation, if you will. And what I've realized over the years is that the engineers who I work with who build beautiful devices, including legged robots, and most recently the one I'll talk about is kind of a limbless snake-like robot, build devices largely to watch them try to succeed in some task and less as dynamical systems which can be objects of study in their own right. As a physicist, I really, in some sense, don't care whether the robot succeeds or fails to go and do some mission. I'm a physicist interested in movement, and these robots provide wonderful systems which I can, in the laboratory, build and systematically test varied parameters to learn what works and what doesn't work in movement, for example, in a limbless snake-like robot on sand. And then it turns out that using those robot models can inform some of the questions in biology that we're interested in. So, for example, we performed a study of a snake, a venomous snake that lives in the desert, in this case in the southwest U.S., called the sidewinder rattlesnake. And it turns out these sidewinder rattlesnakes are called sidewinders because they have this crazy-looking way of moving, which I won't try to describe.
I've seen it. It's bizarre.
It's bizarre, but it's effective. And everybody knows it's effective, but nobody had known why and how it's effective until we came along. And with my colleague David Hu at Georgia Tech here in collaboration with Zoo Atlanta, basically we're able to get 6 of these animals from the desert, ship them to Zoo Atlanta, where we constructed the facility, on-site facility, which is basically a way to create artificial sand dunes in the laboratory, and tested these animals over a diversity of conditions, changing the slope of the hill, and found that they're quite effective on whatever granular material we give them. And using then the robot and the robophysics approach of varying parameters in the robot's gait and how it moves, it's a 16-link robot that can be controlled to move its body in arbitrary shapes over time. We're able to figure out how and why this sidewinding gait is so effective on granular material.
Well, very interesting to hear more about your work, Dan. And we've chatted a little bit about your research, the stuff you're working on today, but I want to know about a success story. Can you share with us one of these successes you've had in your career? It could be recent, it could be a while ago, big or small, whatever you want.
I think that I will tout the success of our recent sidewinding work because to me it's another example of where the kind of intersection of biology and physics and robotics can really serve to advance all three in some sense. So this is the study of these sidewinding rattlesnakes. We studied them in this kind of artificial sand dune test bed, which we create. It's a cool test bed. When my group is introduced to this field, which we basically blow air up through a collection of dry granular material. And above a critical flow rate, the air turns the sand into kind of a fluid-like state, which then forgets any memory of previous disturbances, like previous snake transit. And then if you turn off the air, the sand settles back into a nice loosely packed state of sand. And by pulsing the air to the bed or tapping on it in a controlled way to the bed, you can generate more compact states of granular material. We also can tilt the bed up to 45 degrees and do all sorts of things.
It sounds high-tech and fancy. Yeah.
It's fancy, but it's noisy and loud and kind of all built by us, so it's of the style we like. This happens to be in a little shed that sits out behind Zoo Atlanta. Take the animals, throw them in there, and see what they do. And it turns out we discovered this sidewinding, which seems so complicated and crazy. It's actually the snake is going 30 degrees to the direction you might expect its undulatory travel to take it, is actually a very simple movement strategy and brings in a new idea, we think, at least in biomechanics, in that the animal is generating a wave down its body curvature from its head to its tail. If you just look over its back as it's traveling, that's not surprising. Mm-hmm. But that is actually coupled to a wave in a plane 90 degrees to that, a vertical wave of body bending, which leads to lifting. And if those waves are phased appropriately, then you get sidewinding. And our engineering collaborators had actually known that. They hadn't appreciated that in this way, that sidewinding can be generated by basically the superposition of two waves of body movement. But doing that generates perfectly nice sidewinding in the robot on hard ground. And then the cool idea is that, and we call these things neuromechanical control templates. We have the idea that the organism's, all its complexity is sort of, when it's moving on dry sand, all the complexity of its musculoskeletal nervous system is targeting a particular simple body shape deformation over time. And that effect has some good properties. And it turns out the good properties it has is it basically allows the snake to move on granular materials with very little slip. And if the snake wants to move on granular materials of incline, all it has to do is take that vertical wave, assuming it could independently control it. We can do this in the robot. Take that vertical wave and modulate its amplitude to make the amplitude a little bit higher, which has the effect of making more of the body come in contact with the granular material. And as the hill angle increases, the animals, and it works in the robot, tend to modulate that wave to make more of the body come in contact with the environment. The nice thing about this is that this sort of strategy seems to generate good locomotion performance of the robot on sandy slopes. This was a problem, I should just interject, for the engineers who have been trying to take their robots into sandy caves in Egypt to look for artifacts and were having troubles climbing the little sandy slopes.
Interesting.
The coda to this is that to rationalize this strategy, basically increase your contact length of your body on the substrate as the hill angle increases, it turns out you can do simple physics measurements, drag plates through the sand, which hadn't been done, and it turns out that the scaling of the forces as the hill angle increases works such that if the snake puts more body in contact with the ground, that decreases the susceptibility of the material to flow in just the right proportion, and it all sort of worked out, at least to some first-order approximation. The cooler idea is that you can then, once you have this sort of two-wave template, we call them, this control target, you can think about creative ways to modulate that template to affect other behaviors. And so a postdoc of mine recently has studied the interesting behaviors that these snakes do out in the wild, and we studied in the laboratory. When you scare them or when they want to get away from you, they have kind of interesting ways to turn. It's too complicated to describe, but the video is at our website, which I'll list towards the end, fun to watch. And it turns out that you can think of all these behaviors as really sort of simple amplitude and phase modulations of this base template pattern. And so that, to me, as a physicist, is very satisfying, simple unification of a lot of the complexity we've been looking at in the natural world.
Well, this is really cool work, Dan. I think I have a much greater appreciation of the movement of sidewinders now.
Well, I don't know if I did such a great job, but you can see the videos and it makes it more clear.
Absolutely. Listeners, if you have not seen these snakes move, you have to check it out. Go find videos on Dan's website or on YouTube, something like that. It's really cool. And Dan, now we've chatted a little bit about your work. And in the beginning, we talked about how your life outside of science is quite busy as well. You have a young daughter that you're taking care of. And I think one of the things that scientists like to squeeze in, but oftentimes can't as much as they would like to, is reading. And I love getting book recommendations from scientists. So I'm going to ask you today for a book that you think we should check out. And this can be your favorite children's book of the day, a science book, or a fiction book.
Well, I read each night. And some nights a little bit, and that puts me to sleep. and I try to read fiction, nothing very highbrow these days, mainly science fiction. These days I've been reading, honestly, history of technology in some sense. There's the Isaacson book called The Innovators, which is a very interesting book, which goes from Ada Lovelace to one of the early pioneers in computation, to Babbage, to Turing. And that's been a nice book. I've been thinking about these issues as we've been working on this RoboPhysics review article, largely because I think that the kind of ideas we're addressing in this RoboPhysics is really questions which are at the general principle level of trying to understand movement. And I have some sense that the integration of science and engineering is critical for such studies. And I've been sort of interested in the integration of science and engineering in the early days of computing, computer science. That's something I've been reading. I should also mention that I read per day more books about Peppa Pig and Maisie's Plane than I do. If you have kids, those are books if they're under 22 months.
Fantastic. Well, great recommendations for all of our listeners out there, even if they're young ones. And I love reading these books about science and the history of science and technology. I think it's so cool to kind of look at how far we've come and then sort of project then forward on how far you think we can go. So great to get your recommendations. We'll put them up on our website. And one thing we haven't yet really touched on in our discussion today is travel. And I think this is a big part of the career of a scientist. And perhaps some of the listeners out there, some of the public out there might not realize how big of a role it plays. So can you share with us, Dan, what you think is your favorite place you've been to for science?
I think this is an important aspect. And my wife, who's not a scientist, did not realize this when she married me.
She didn't know what she was getting into.
That's right. A good chunk of my life is on the road. And even if I'm not on the road, I'm preparing to go somewhere. There's that component to science, which I had no clue about till I got into the business. The privilege of this life is that one gets to meet people and interact with people from all over the world and visit them. And it's just a wonderful aspect to this. Not only the places you go, but the people you meet. My, I'd say, favorite experience in the last 5 years was one in which I went to Africa, to Cameroon, to participate in a international hands-on school. It was, in fact, set up by my PhD advisor, and he roped a number of his former students and postdocs in to kind of participate as faculty in the school. And basically, we went for 2 weeks. I brought some all-star graduate students along with me. Went for 2 weeks, and we did hands-on biomechanics experiments. There were 12 faculty, and each of us for 2 weeks got to do something that he or she thought was interesting and could be communicated, some experimental work that could be also performed on a budget that someone in a developing country could conceivably attain. I think the philosophy of the school is that a lot of what's done in countries where the infrastructure for experimental science may not be as strong as in, for example, the U.S. or Europe, people tend to fall towards theoretical work, thinking that experimental science is just too expensive or impractical form. And that may be true, but there's certain problems in science, and I think I'll tout these biomechanics problems and robophysics problems, which are robotics is increasingly the domain of high school students who every kid I get at Georgia Tech in the engineering school wants to build a robot, can now with the advent of 3D printers and low-cost Arduinos and electronics. So with this school, we went to Africa, and for 2 weeks, basically got to perform biomechanics experiments, built a low-cost force plate, which is a device which measures the forces in 3 orthogonal directions on your feet as you walk or run across it. And we're able to reproduce some of the classic studies in ground reaction force pattern changes as you go from a walk to a run, all for under a couple $100, whereas existing force plates can cost $10,000.
Oh, wow. That's awesome.
That was a lot of fun.
Well, I love this theme of hands-on science, and I think that takes you back to that quote that you mentioned towards the beginning of our interview. So can you share with us, what was one of these memories that really stuck with you for that experience? Was it building the force plate? Was it interacting with the students? Tell us a little bit more about it.
It was all of the above. My students in my lab, particularly a graduate student named Nick Gravish, a really critical enabler of this trip in the sense that he and I chatted and said, boy, wouldn't it be neat to be able to do some of these experiments on a budget? The idea is you don't have to spend $10 million to do cool, cutting-edge experimental science. It's available to you and increasingly available on $10,000 and others more. But these kind of budgets can even produce interesting stuff. And so we cooked up a design of a force plate that could do the job and put together some simple low-cost electronics. And there were computers available, and we designed this and then packed it in a big red suitcase and flew it to Paris and then to Douala in Cameroon, and then took a bus to Boya, which is a little town where there's a big university, and we set it up and had a local carpenter make the ramp and trackway that we embedded the forced platform into. And he turned out to be a very nice guy, and they didn't have electricity in the town on occasion for some chunks of the day. So he actually cut all the wood by hand himself, assembled the forced platform, and we had students from all over Africa who had attended this school, walking and running and recording forces. We even did a little side module of which we recorded EMG, surface electrodes, to record electromyographic signals, the electrical signals coming from contracting muscles for students as they were flexing their muscles or doing push-ups. And so it was really sort of a fun, low-cost, but eventually valuable biomechanics exercise.
Well, this sounds like a phenomenal initiative and a really wonderful way to spend a summer. So thank you so much for sharing your experiences. And I think it was wonderful to talk about the people that you interact with in science. And this is something you sort of mentioned through describing this memory. And I think in science, you get to work with a variety of different groups of people as you go throughout your career, going through different laboratories, and each kind of has its own personality and often some quirky traditions or memories that come with it associated with that group of people that you were with at the time. And I love showcasing the human side of science because we're not little robots that go into the lab every day, do our work, and go home.
Not yet.
Not yet. But we like to have fun too and enjoy the company of the people we're with. So Dan, can you tell us about one of your memories of the fun side of science?
Well, to me, doing the science is just sort of inherently fun.
All sides of science are fun, right?
Yeah, I mean, it's almost a definition to me in some sense. I will say that from my personal taste, and I will not give too many details because it's too embarrassing, but as a graduate student, I had a lot of fun being in a band in Austin, Texas, composed of 3 of us in Harry Sweeney's lab and a friend of mine outside of science. And we spent in our quote-unquote spare time rehearsing and then playing clubs around town. And the nice thing was that most bands in our city, we were not very good. In many dimensions, we were not very good, but we enjoyed it. And the great thing was that Sweeney's lab was rather large, lots of graduate students, lots of postdocs. In particular, his Center for Nonlinear Dynamics was rather large. And so unlike other bands of our ilk, we could draw a big crowd for sort of arm twisting and promise of free drinks.
Mandatory lab outings, right?
Correct. And we filled up lots of low-rent bars in Austin with scientists who did not always make the owner of the bar happy, because the scientists we knew tended to be more on the conservative side of what the bar owners would like. But at least there were warm bodies in the place. And so some of my fondest memories from graduate school are actually on a weekend doing that, having the people we knew come out and have fun and listen, suffer.
Clap you on, yeah.
Well, clap is a kind word.
That's right. Were you the guitarist of the band then?
I was not the guitarist. I wanted to be the guitarist, but I got stuck being the singer.
Gotcha. Well, wonderful to hear about the fun side of science. One of these memories from your past where you were able to get together outside of the lab and have fun with people. And I think that's a big part of science as well, as the bonds you form with the people that you work with, even if you're dragging them to the bar to listen to you in your band late at night. So great to hear about your memories and your experiences. And I think we've chatted a lot about the research, about your life today as a scientist, but we haven't yet talked about the questions that you have yet to answer. And I love to hear about these big questions that scientists have in their mind. They're sort of their dream questions. So Dan, today we are going to hypothetically give you everything. So funding, staff, technology, feasibility, not a problem. What do you want to answer?
Oh man, that's a scary question, because I think, as much as it pains me to say this, having funding, staff, technology, feasibility constraints actually makes me do better science. I'm not going to evade your question, but I think that somehow science is the art of the soluble. There's a famous quote to that. And having these constraints de-scopes things so that you actually have to get something done.
Right.
That's not a good answer to your question.
I'll keep pressing.
It's an honest answer to your question. But if I didn't have to write a grant and I could just be given, Bill Gates came and said, here's $10 billion, do what you will, I would probably try to move into the realm of astrophysics, in the sense of I would want to try to make exotic states of matter in the laboratory and do laboratory experiments on things like black holes. Now, that's total science fiction kind of stuff. But I've had a layperson's interest in astrophysics and cosmology since I was a kid. Mm-hmm. Took some classes in graduate school and would love to work on that stuff. The problem is that stuff. I would love to work on
technical term, yeah,
on problems associated, but somehow I'm tied to the land. I need to have it on the tabletop where I can manipulate it systematically, vary parameters. So I would want to do kind of the nonlinear dynamics of black holes and throw things into them and poke them and test the theoretical predictions, which have been made over the years, and see really what a singularity is made of somehow. Because that seems to me just total mystery. Suddenly you say, well, the laws of physics no longer work. I don't know. That seems to me something that's just crying out for laboratory experiments. But I have no idea how to do it and no funding to do it, and et cetera, et cetera. And I don't want to have to go to a Large Hadron Collider, which could hypothetically make and spend billions of dollars to have to do it. I'd want to have something on the tabletop.
Well, I love it. I love that you've thought big with us here, Dan. And I think this idea...
Sorry.
No, it's great. I think a lot of people get stuck within the constraints of this funding staff, technology, feasibility, things that they already know how to do. And I love that you're stepping outside of that with this hypothetical question, wanting to build this benchtop black hole experiment to really understand some of the fundamental properties of the universe. Fantastic question to answer. So now that we've dreamed big, Dan, we're going to step back and think about your career as a whole and all of the people who you've encountered along the way. And I want you to share with us the best piece of advice you've ever received.
I think the best piece of advice is probably from Max Perutz, who I met as a high school student. And as I mentioned, leaned in and said, find a good mentor. I wish I could give a better bit of specific advice on that, but I think that everything flows from that. And I think that can be interpreted in many ways and is sufficiently general and vague and flexible. And it comes from a Nobel Prize winner, so it's
got to be good, yeah.
I can punt a little bit on that. But honestly, I have to say that's the best advice.
Fantastic advice for our listeners. Find a good mentor. Now, Dan, can you tell our listeners how they can reach out to find out more about you and your work?
Sure. If you go to Google and type Dan Goldman, Georgia Tech, that does the job. If you want to go to my lab's website, crablab.gatech.edu, crablab.gatech.edu. CRAB stands for Complex Rheology and Biomechanics, which is a title we gave the lab way back when.
I like it.
Or you can email me, daniel.goldman@physics.gatech.edu.
Perfect. Well, listeners, definitely reach out if you have any questions for Daniel. Learn more about what he's working on. And Dan, thank you so much for joining us today.
My pleasure. Thank you for doing this. Wonderful, wonderful program.
Well, it was a pleasure to chat with you. And listeners, thank you for joining us today. We'll see you next time on another episode of People Behind the Science. Your voyage to the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to seeing you next time on People Behind the Science.